Good day, students. So in this recorded lecture video, we will continue discussing the lecture 13, the UV transformation, the change of variables. So yesterday, we have started this lecture 13, discussing how to transform the equations into U and V, and then to solve this double integral problem using the UV transformation. So just to recap a few things to keep in mind in this lecture 13 about the UV transformation. So once again, you should still be able to recognize a pair of a similar function in both the variable x and y. As we have seen a few examples in the previous lecture video, you will always be given 4 different functions, and from these 4 different functions, you recognize the similarities, and then you group them together, change it into U and V. Now again, when we're talking about the UV transformation, make sure in the end, all the variables x and y will fully be transformed into variables U and V. And that you should also remind yourself there will be the Jacobian transformation computation that you need to perform, which involves the partial derivatives. And take note that inside the double integral, the Jacobian is always a positive value. Now, again, these are the 2 techniques that you can refer to when finding the Jacobian determinant. Like we mentioned yet in the previous lecture video, if your function is in terms of x equal and y equal as the main subject, then we use this first technique in finding the Jacobian. On the other hand, if your function of transformation is u equals and v equals, then we use the second technique 1 over to find out the Jacobian determinant. So take note that under the Jacobian determinant computations, we still consider the partial derivatives. So let's continue discussing more examples on how we can solve the problem involving the UV transformation. So this is taken from the past year questions, February 2024. The question sounds like this. The region R is enclosed by the lines y equals to x plus 1, y equals to x minus 2, y equals to 1 minus 2x, and y equals to 3 minus 2x. Use an appropriate transformation to evaluate the double integral x minus y over x plus 2, y plus 2x with respect to area A. So here, the question highlighted the appropriate transformation, which means you are the one who will assign the u and v into a proper function. Now, as usual, we first collect all the 4 equations and see how we can analyze them. So first, y equals to x plus 1. Second, y equals to x minus 2. Third, y equals to 1 minus 2x. And finally, y equals to 3 minus 2x. Now, if you look carefully, this equation consists of both x and y on different left and right hand side. So one thing that you can do is you first by rearranging all the equations in such a way that all the variables should be grouped on one side. So since look carefully here, y equals to x plus 1. So now I can rearrange and say that this is actually x minus y equals to -1. Again, if I rewrite that, net plus 1 here, and variable y, we swap the position, giving you -1 equals to x minus y. Here, on the other hand, if you swap -2 and y, this gives you 2 equals to x minus y. On the other hand, for this case, -2x, we swapped to the other side, giving us 1 equals to 2x plus y. Same goes to here. This can be rearranged into 3 equals to 2x plus y. Now, this should be the first step. That is, when you are given all the 4 equations in which all the variables are scattered around, then one step is that we group all the variables on single site first. Then from here, we can see the similarities. So here, you will notice that x minus y are the same here. Therefore, I can now let my transformation u be x minus y. Because the first 2 pair, I let it be u. So now the next pair, I let it be v. That is v equals to 2x plus y. Again, from this step, we try to rearrange all the variables such that x and y are both on the same sides, leaving constant on the others. And then once you found the similarities in the pair of equation, x minus y, therefore now you can let it be your u, and the remaining pair, 2x plus y, you can let it be v. So this will immediately gives you the bound u equals to -1, u equals to 2. Similarly, here gives you v equals to 1 and v equals to 3. So this, when you try to combine, it gives you the integration from -1 to 2 du. This will gives you the integration from +1 to 3 dv. So this is the first step on recognizing a pair of similar functions, transform it into u and v. Now, in the second step, we are going to compute the Jacobian transformation. That is the j of x, y variable transformed into u and v. So this is the determinant of 1 over differentiate u with respect to x, differentiate u with respect to y, differentiate v with respect to x, differentiate v with respect to y. Now look carefully. Previously, our u function is x minus y. Our v function is 2x plus y. Therefore, upon the partial derivative, let's analyze one by one. Differentiate u with respect to x. We obtain 1. Differentiate u with respect to y. We obtain -1. Differentiate v with respect to x. We obtain 2. Differentiate v with respect to y. We obtain 1. So this determinant upon computation, remember the cross multiplied subtraction, 1 multiply 1 gives you 1, minus 2 multiply -1, we have -2. So in the end, the Jacobian determinant is +1 over 3. Now, once you have the Jacobian second step ready, we can now consider the original function, the double integration of the region R with respect to the function x minus y over y plus 2x with respect to area A. So this can be retransformed into double integral in du dv, such that my u interval previously -1 to 2. And my v is from 1 to 3. X minus y, we have transformed it into u over y plus 2x is just the same as 2x plus y, the same notation, transformed into v. And finally, do not forget the absolute value of your Jacobian transformation. So this is just a simple integration. As usual, 1 over 3 is a constant positive number, which we can put it out. And that integrating u with respect to u, this gives us integration from 1 to 3. 1 over v still remain untouched, and we have u is integrated into u squared over 2, substituting upper limit 2 and lower limit -1. So this integration and substitution should be straightforward. Integrate 1 until 3, 1 over v in the big bracket, substituting 2 into it, 2 squared divided by 2, minus, substitute -1 into it, -1 squared over 2 is positive 1 over 2. So this computation in the end gives you 1 over 3 integration 1 to 3 of 3 over 2 multiply 1 over v. Well, of course, I hope you can see that this fraction can actually be simplified, giving you 1 over 2 integration 1 to 3, 1 over v dv. So the final integration 1 over v should gives you ln. Remember, integrating 1 over v gives you ln v, integrated upon upper limit 3, and lower limit 3. So in the end, this gives you 1 over 2. In the big bracket, substitute 3 into it. We have ln 3 minus substitute 1 into it. We have ln 1. And remember, ln 1 equals to 0. So in the end, this substitution and computation yields ln 3 over 2. So once again, you can see the main point of the UV transformation still lies on the technique of grouping a pair of similar equations and transform it into new variable u, group another pair of similar equations, transform it into v, and this UV transformation, later you will use it to compute the Jacobian determinant. And this Jacobian determinant can be positive, can be negative number, and which upon into the double integral transformation gives you integration in both u and v variables. Now let's see more example to see how we can play more with the UV transformation here. Again, July 2023, past year questions. Now use the transformation u equals to x plus y and v equals to x minus y to evaluate the double integral x minus y in the bracket, exponent power x squared minus y squared with respect to area, where R is the region enclosed by the line y equals to -x, y equals to 1 minus x, y equals to x minus 1, and y equals to x minus 4. Now, since again in this question, you are already been given the transformation u and v, which means we will try our best to rearrange these 4 equations so that we can reach either u or v structure. So again, let's consider the y equals to -x. If you try to rearrange this equation by putting -x to the left-hand side, we have x plus y equals to 0. Similarly, y equals to 1 minus x. If you try to rearrange negative x to the left-hand side, you reach x plus y equals to 1. So here you can see that x plus y initially has been given transformation u. So this means u equals to x plus y, and this gives you the value u0 and u1. In other words, the integration from 0 to 1 with respect to u. So if the first two pairs has been taken by u, you should know that the next two will be taken by v. So the next two equation, y equals to x minus 1. So this time we want it to be x minus y. So therefore, we swap these two integer and variable, negative 1 and y, we exchange their position. So now 1 equals to x minus y. Similarly, y equals to x minus 4. We change minus 4 and y. Now 4 becomes x minus y. So therefore, in this case, clearly we have x minus y and x minus y. This is actually our v. And that v equals to x minus y, which means v equals to 1 and v equals to 4. This gives you the integration from lower limit 1 to upper limit 4 with respect to v. So this is, again, the first step. As for the second step of the Jacobian transformation computation, similarly, we want to compute Jacobian determinant of variable xy transformed into u and v. By the formula, it should be 1 over the determinant of partial derivative del u over del x, del u over del y, del v over del x, and del v over del y. Because all our u and v are the main subjects here. So this gives you the computation of the determinant. So once again here, differentiate u with respect to x, 1. Differentiate u with respect to y, also 1. Differentiate v with respect to x, 1. Differentiate v with respect to negative y, we have negative 1. And therefore, by the cross multiply and subtraction, 1 multiplied by negative 1, we have 1 over negative 1 minus 1 multiplied 1, 1. So the Jacobian determinant is negative 1 over 2. Take note that, as I mentioned in the previous slide, your Jacobian determinant can be positive, can be negative numbers. So don't worry about this. Now, once we have transformed u and v accordingly to obtain the interval of du and dv, we have also performed the computations for the Jacobian determinant. Now it's time for us to deal with the problem in the original double integral questions. So here, originally, we have double integral with respect to the region R in the big bracket x minus y exponent power x squared minus y squared with respect to area A. Now, under this case, we will open double integral again for the UV transformation, du dv. So in such a way that du interval is 0 to 1, dv interval is 1 to 4. Now, transforming x minus y. Previously, we have x minus y equals to v. Exponent, what about x squared minus y squared? Now, since we mentioned in the UV transformation, every variable x and y must be fully transformed into u and v. So far, x minus y, we have transformation v, therefore it can be replaced by v. But x squared minus y squared, if you look at the transformation u and v, they are nothing the same. So what can we do in this case? Now, if you still remember yesterday, I did mention, whenever you notice that there is something that you cannot directly transform from u and v, what you can do is try to multiply this uv together. Again, if you notice that the function x squared minus y squared cannot directly be transformed from u and v itself, what you can do is maybe you can try to multiply u, v together. Because if you multiply u, v together, you will notice that this is just x plus y multiply x minus y. Now try to expand this equation and see. X multiply x, x squared. X multiply negative y, negative xy. Positive y multiply x, positive xy. Positive y multiply negative y, negative y squared. And that from here, you notice that minus xy plus xy can be eliminated, and that this gives you exactly what you need, x squared minus y squared. So which means now this transformation at the exponent power here is actually uv. So finally, after transforming the whole x and y into u and v, do not forget you need to multiply with the absolute value of the Jacobian determinant. So that's why, like I said, if you obtain a negative number in your Jacobian determinant, you don't have to worry too much because upon the absolute value, it will actually transform it into a positive numbers. So let us tidy up a bit this notation in the next step. Integrate from 1 to 4. Integrate from 0 to 1. This 1 over 2, if you prefer, you can immediately pull it out. So it gives you uv exponent uv du dv. Now, since we are going to integrate with respect to u first, so exponent uv du. So not sure if you can see carefully, you are going to integrate exponent uv with respect to u. So this should gives you 1 over 2 integrate 1 over 4. V it's not related, therefore pull aside, but integrating exponent power uv should gives you exponent uv over v, substituting 1 and 0. Now, I'm sure at this point, some of you may confuse. Why is that when you integrate exponent power uv, we obtain exponent uv over v? Now, let me emphasize again under integration. Since we integrate with respect to variable u, we assume v is a constant. Again, because we are integrating variable u, we will assume v is like a constant. Now, recall yourself to previously when we learned integration, integrate exponent power 2x. We say that this integration gives us exponent 2x and then divide by 2. So notice that this value 2 is actually taken from the coefficient of exponent. Therefore, this v is also taken from the coefficient of u, because integrating with respect to u, v is assumed like a constant. So here you notice that variable v and variable v can be simplified. And that upon the substitution 1 until 4, substituting 1 into it, we obtain e power v. Minus substituting 0 into it, we have e power 0 dv. Take note that exponent power 0 actually gives us a constant identity value 1. Again, take note exponent power 0 equals to 1. So from here, the next integration should be straightforward because we are integrating it with respect to v. Exponent v, if you integrate, you get back exponent v, the same function. Minus, integrating 1, you obtain variable v. So upper limit 4, lower limit 1. So your last step should be the substitution using upper lower limit. So substituting upper limit into it, we have exponent power 4 minus 4. Subtract, substituting 1 into it, we have exponent power 1 minus 1. So simplify this expression a bit. 1 over 2 in the big bracket. Exponent power 4 is a constant number. Minus 4 minus negative 1, we have minus 3. Minus exponent, just minus exponent. Now, since all these are a constant number, if you do not wish to change it into decimals, you can just remain them in the original form. So again, this is the transformation of uv from the variable x and y. Now, this question again will emphasize to you further under certain conditions. Thus, u and v will be given earlier, and that all the equations that you have now, you just need to transform and rearrange until you have the same u, v structures. Second, when you compute the Jacobian determinant, again, this value can be positive number, can be a negative numbers. So when you put into the transformation double integral, upon the absolute value, negative will become positive. Third, when you transform the function xy into u and v, sometimes you cannot directly transform it using u and v alone. Like in this case, u alone and v alone cannot give you x squared minus y squared. Therefore, you may need to combine u, v together and see whether you can get a desired result. And lastly, the fourth point, when you have the functions involving several variables, make sure you still remember when you integrate with respect to one variable u, the variable v is assumed to be a constant. So if you are clear with this, then hopefully I will demonstrate to you one more complete examples on how to do or how to perform the UV transformation solutions. Again, the examples in February 2023 past year questions. Again, this time, you are already being given the transformation u equals to 5y minus 2x and v equals to 3x plus y. And you want to evaluate the integral, double integral, 1 over 3x plus y squared with respect to area A, where R is the region enclosed by the line, 2x equals to 5y minus 1, 2x equals to 5y minus 3, y equals to 1 minus 3x, and y equals to 4 minus 3x. Similarly, this transformation u and v has been given. Therefore, we stick to these two transformations and rearrange the four equations. The first equation, 2x equals to 5y minus 1. Now, upon rearrange, -1 and 2x. Swap these two positions. We have +1 equals to 5y minus 2x. And now you see the structure of u. The second equation, similarly, 2x equals to 5y minus 3. Upon rearrange, we have +3 equals to 5y minus 2x. Again, variable u. So these two is a pair. So u equals to 5y minus 2x. So that now your u equals to 1 and u equals to 3. Combining them, now your interval of integration from 1 until 3 du. On the other hand, the next pair, y equals to 1 minus 3x. So what I will do here, I will just move -3x on to the left-hand side. So this gives you 3x positive plus y equals to 1. Similarly, y equals to 4 minus 3x. By moving -3x to the left-hand side, I have 3x plus y equals to 4. So this will give you the transformation of v. V equals to 3x plus y. And this gives you v equals to 1 and v equals to 4 in such a way that if you combine them together, the interval of integration is from 1 to 4 dv. So this is again the step. Second, again, Jacobian transformation. The Jacobian determinant of x, y into u and v is again given by 1 over to the determinant of partial derivative del x over del u. Oops, should be the other way around. Differentiate u with respect to x, differentiate u with respect to y, differentiate v with respect to x, and differentiate v with respect to y. So this has the partial derivative 1 over the determinant. Differentiate u with respect to -2x, we have -2. Differentiate u with respect to 5y, we have y. Differentiate v with respect to 3x, we have x3. Differentiate v with respect to positive y, we have 1. So again, upon the cross-multiply computation, this gives us 1 over -2 multiply 1, -2, minus 3 multiply 5, 15. So in total, -1 over 17. So as I mentioned, your Jacobian determinant can still be a negative numbers. All right, everything has been done. Next, we deal with the original questions, the double integral. So the double integral originally, the questions, double integration of region R, 1 over in the bracket 3x plus y squared with respect to area A. So this is the same as we open double integral for the transformation in u and v in such a way that du has the interval 1 until 3, dv has the interval 1 until 4. 3x plus y is given by v. So this is just 1 over v squared. And don't forget the Jacobian term modulus negative 1 over 17. So since negative 1 over 17 will becomes positive under absolute value, so in the next step, you can pull out this constant coefficient 1 over 17 first, and then perform the computation of integration. Since we first integrate with respect to u, again, since we first integrate with respect to u, there's no variable u currently. So which means 1 over v squared is still a constant. Integrate with respect to u, we obtain the new variable u in it from 1 to 3. So this can be evaluated using the upper-lower limit. 1 over 17 integration 1 to 4. 1 over v squared still remain here. But here, when we substitute 3 into it, minus substitute 1 into it, we get just a very simple constant number 2. So these two, I can pull out 2 over 17, integrate 1 over 4. 1 over v squared, again, 1 over v squared, we change it into index law, v power negative 2. So that you are aware, when you try to integrate v power negative 2 with respect to v, what you will obtain is v power negative 1 over negative 1. Now, if you can't see it, no worries. We try to change the notation a bit. V power negative 1 over negative 1 is actually negative 1 over v. 4 and 1. So finally, replace upper limit into it. We have 2 over 17 in the big bracket, negative 1 over 4 minus negative 1. So this gives you 2 over 17. Negative 1 over 4 plus 1, we have positive 3 over 4. So this gives us, in the end, 3 over 34. Now, once again, as you can see here, for all the problems involving UV transformation, eventually, in the end, you will obtain a fixed number in the output, because both U and V, the interval, are actually a fixed integers. Now, we have gone through 3 different examples in the full demonstration on how to transform equations into U and V, performing the Jacobian determinant, and next transform the double integral problem to solve it. So in the final example in this recording video, July 2022 questions, I will only help you to set up the double integral, and the other working steps, I will leave it to you as your own exercise. So this is July 2022. Now, just to let you know, this question may be slightly challenging at first, because somehow your mind needs to be twisted a bit for you to catch the idea of xy into uv. The question sounds like this. Use the transformation x equals to v over 6u and y equals to 2u to evaluate the integral x y power 3 with respect to a, where region R is bounded by xy equals to 1, xy equals to 3, y equals to 2, and y equals to 6. Now, under these 4 different equations, suppose the one that will easily drag your attention should be y equals to 2u, because you immediately can find the identical pair here. So we begin from this 2. So y equals to 2u. If we try to slightly rearrange it, u equals to y over 2. All right, now if you look carefully in the equations that you have, y equals to 2 and y equals to 6. So using this u equals to y over 2 and y equals to 2 and y equals to 6, when you substitute into it, you will notice that u equals to 2 over 2, 1. See, this y is replaced by 2 and next by 6. So here, this gives you u equals to 6 divided by 2. That gives you 3. Combining everything, this gives you integral from 1 to 3 du, because u is the transformation y over 2. Now, xy equals to 1, xy equals to 3 may not be obvious at first. Okay, indeed, it may not be too obvious, but here we have x equals to v over 6u. Again, we repeat, here we have x equals to v over 6u. Now, I'm not sure if you notice carefully, 6u is actually 3 multiplied 2u. In other words, I can try to rewrite this statement as v over 3 multiplied 2u. Why is this so special? Because 2u is actually y. Therefore, I can rewrite this as v over 3y. If you understand this, by putting 3y on the other side, so now it gives you v equals to 3xy. Again, the trick is that 6u, you split into 3 multiplied 2u. Because 2u is actually y, therefore this 3y, if you shift to the left-hand side, 3xy equals to v. So if 3xy equals to v, so now you have xy, oops, let me change using the same color. So from here, you have xy equals to 1, xy equals to 3. So substitute this position xy with 1 and with 3 to obtain the interval for v. So this gives you v equals to 3 multiply 1 which is equals to 3. Here gives you v equals to 3 multiplied 3 gives you 9. In other words, combining this gives you the interval from 3 to 9 dV. So now you have the two transformation u, v. So this is the first step in tracing what is the lower upper interval for u and v transformation. So in the next slide, second, we need to compute what is the Jacobian determinant. From variable xy, we transform into u and v. So this is the formula 1 over in the determinant, del u over del x, del u over del y, del v over del x, and del v over del y. So just now, we have the wave function u equals to y over 2, and v equals to 3xy. So upon the Jacobian determinant, we have 1 over determinant, differentiate u with respect to x. There's no x variable here, therefore the differentiation should be 0. Differentiate u with respect to y, we have 1 over 2. Differentiate v with respect to 3xy, we actually obtain 3y. Finally, differentiate v with respect to 3xy, we have 3x. So this computation later gives us 1 over 0 multiplied 3x, 0 minus 3y multiplied 1 over 2. We have 3y over 2. So this is 1 over negative 3 over 2y. We still have the variable y here. But take note that initially y equals to 2u. Therefore, from here, 1 over negative 3 over 2 multiply 2u. Lastly, you obtain the Jacobian determinant negative 1 over 3u simply. Now, no doubt, this is getting slightly confusing because we can transform again all the variable y's in the Jacobian determinant into u. So now this is the full Jacobian determinant that you need. So once everything is done, then we can put everything into the original problem. This is a double integral for the region R, such that we want to compute what is x, y power 3 with respect to area A. So this is again open double integral for du dv. Previously, we have found the interval of u is from 1 until 3. The interval of v is 3 to 9. What about x, y power 3? For this case, let me borrow a bit of the functions of uv that we found here. U equals to y over 2. V equals to 3xy. So u equals to y over 2, we can clearly say that this y equals to 2u. Similarly, v equals to 3xy. Oops. So from this equation, I can slightly change that xy equals to v over 3. Now, if you started to catch something here, very well, because you will notice that x, y power 3, I can rewrite this as x multiply y squared. Again, I can split xy power 3 into xy multiply y squared. So xy is actually v over 3. Y squared is actually 2u squared. So combining everything, this gives you 4u squared v over 3. 2u, if you square it, it becomes 4u squared. So which means this part here is transformed into 4u squared v over 3. Don't forget, we still have the Jacobian determinant, modulus negative 1 over 3u. And so happen again, in this case, u squared and u can be eliminated. Whatever is left, 4 over 3 multiply 3, 4 over 9, you can pull it out. Now this double integral is simply from 3 to 9, from 1 to 3, u, v, du, dv. So this is just a simple integration. From here, you can continue further on your own. And in the end, you obtain a very nice solution 64. So this is how the setup of the UV transformation for this double integral. Now, again, this lecture 13 of UV transformation, basically, the most challenging part in this topic is how you actually manipulate, rearrange, and transform the variable x and y into totally u and v. For the kind of the transformation from xy into uv, sometimes the process can be straightforward, just like what we have seen in the previous example, like in this case, 1 over 3x plus y squared. 3x plus y is already v. Therefore, we simply transform it. Sometimes the transformation can be indirect, not obvious. Just like in this case, we have x squared minus y squared, which is not directly from u and v alone. Instead, u multiply v. Even more challenging, like in the questions that we discuss now, x, y power 3. You have to somehow rearrange your u, v, and x and y so that they tally and achieve the transformation that you are looking for. So the only advice under UV transformation is through practice. You need to practice a lot for you to be able to twist and brainstorm your mind quicker how to rearrange the mathematics and equation to achieve the transformation that you want. There are many exercises in this lecture 13. Try on your own, try and see whether you can reach them. Now, in the next example, February 2022, okay, just to take note here, this question is indeed challenging. You can try on your own first, but if you fail, don't worry. Try to refer to the solution scheme that I will attach later and see how much you can understand the process. And of course, many tutorial questions have been prepared for you to practice yourself. Now, these are all about the UV transformation for lecture 13. Indeed, Your coming common test is only tested up to this topic. So make sure after this, do more revision, practice more questions. Any questions, don't be afraid to reach me anytime. That's it for the asynchronous lecture session for this hour. Thank you and see you.